Hello everyone. This is a follow-on to the very interesting talk that Professor Donkelman, Peter, just gave. So Peter, that was a very nicely put together talk. Thank you. I enjoyed it. And the way I've put this together, and I didn't even until this morning I was still thinking about what exactly I was going to do in this problem session. What I'm going to do is I'm going to sort of break this up into two things. And the first thing, I'm going to talk about some problems that Peter suggested based on what he spoke about in his talk. And so and these problems I think are interesting because they serve to illuminate how you go about thinking about problems in this area and show some of the standard tricks that can be used in dealing with this kind of stuff. And then the second thing I'm going to do is I'm going to show you what I'm 99.9% sure is still an unsolved research problem that comes out of a paper that I wrote with Peter and some other people some years ago, and which is now at the stage of having been accepted for publication, but not actually appeared in publication yet. So let me start off, and I've got two different things here. So if you look, there's like two David Erwins in the chat at the moment. There's me and there's my evil twin, also known as my tablet. So I'm going to start off by sharing my screen of the first me. And I have a suspicion the dogs are about to start barking. Oh my goodness, okay. If that happens, I apologize in advance. Can everyone see that?
Yes, we can.
Okay, fantastic. So let me go down. Okay, hang on. My apologies, colleagues. Just give me 30 seconds. I just have to sort this out. Okay, my apologies for that. I guess the dogs didn't like the structure of the problem session I was suggesting, and so they decided that we're going to go somewhere else, each to their own. So let me just see if I can page down here. So these are the problems I mentioned, which are problems that Peter suggested based on some of the things he talked about in his talk. And some of them are things he explicitly mentioned, and some of them are sort of inspired by things he explicitly mentioned in his talk. So I don't quite know what the right way to go about doing this is. I mean, should I just put these up here and wait a few minutes and let people think about these things and then we talk about them, or should I just sort of launch straight in and say, you know, this is one way in which to talk about these things? Mafunda, do you have a preference? I don't.
I don't have any particular preference, but to have them shown on the screen for a little bit longer is a good idea, because it allows us to actually read through the question or think of the problem.
Okay, it sounds like you do have a preference. Fair enough. Okay, so let me just leave this there for a couple of minutes, and so have a look at those and think about them. And of course, there will be people in the room who know exactly how to do these things, and there are people who haven't looked at these before. So have a think about that, and then in a few minutes I'll come back and we can start talking about these things and how you might go about thinking about them. And in the meantime, I'll switch my video and everything else off. Okay, so I hope those of you who haven't seen these problems before know exactly how to do them, have had some chance to think about them. Let me start, and I hope everyone's written this down, because what I'm going to do now is I'm going to switch over from sharing the screen on my PC, which is showing the slide, to sharing the screen on my tablet so that I can write things down. So let me just stop that share. There we go. And then let me come in here and say, there we go. Okay, so I hope that's visible. And I've got to move this thing. Okay, there we go. Don't want that either. Well, let's just, so I'm just trying to figure out where to, there we go. Okay, minimize this zoom panel that appears in the middle of the whiteboard when you're trying to write, and it just always seems to be in the wrong place. So in this first problem, so where's the color? Okay, so we want to prove that if you have a connected graph of order n, then n plus 1 over 3 is an upper bound on the average distance, and that's the same thing as the average distance of a path of order n. So in other words, the path of order n, as Peter indicated in his talk, is the worst case that can happen when you're dealing with average distance. So let's start off with the second thing, with the right hand side over there. So I mean, if one wants to show that the average distance of Pn is n plus 1 over 3, then what you can do is, so here's my path, right? So it is there, and so there's v1, v2, v3, v4. This is vn minus 1, vn. And what I'm going to do, and so Peter talked about this as well, is start off by working out the sum of all the distances between the vertices in this graph, the Wiener index. And then once we have the Wiener index, then we can just divide by n choose 2 to get the average distance. So Peter did an example of this in his talk, when he worked out the average distance of that small path. I think it was P4 or something. And what he did when it was add up, you say how many pairs of vertices are at distance 1, how many pairs of vertices are at distance 2, and so on. And you can do that. I'm going to do things a slightly different way, show you a different way to do that. And so what I'm going to do here is start off by saying, if you look at, get blue, if you look at V1, this left-hand end vertex over here, and say, what are the distances of the vertices from it? Well, this is distance 1 away, distance 2, distance 3, distance n minus 2, and distance n minus 1. So the sum of all the distances of the vertices so over all x, the sum of the distance from v1 to x is 1 plus 2 plus, and so on, which of course is n times n minus 1 over 2, or n choose 2. Okay, so that gives us the sum of all the distances from v1 to everything else. How do we do the rest? Well, exactly the same. What we do now is we now move to v2, and what we're going to do is we'll just add up the distances in v2 to all the things on the right hand side of it. And the reason we do that, of course, is because you don't want to count a distance we've already counted before. So if we now work out the distance, the sum over all x of the distance from v2 to x, where we're counting on the right hand side. So I should say, x to the right or something. Then we get, well, the same thing, 1 plus 2 plus 3 plus, but now we stop at n minus 2. So this is n minus 1 choose 2. And so we keep going like this. And so what we'll eventually wind up with, if I move this up the top here, so let me just, oh my goodness, okay, hang on. So I need to move. There we go. So I'm just going to bring your attention back up to the top here. And so we have the Wiener index is, so n choose 2 plus n minus, whoops, not n minus, whoops, n minus 1, but just give me a second here. Where's undo? N minus 1 choose 2 plus n minus 2 choose 2 plus, and then eventually we get down to these last two vertices over here. So that, you know, that's 2 choose 2, which is the same as 1. And then there's a reasonably well-known identity involving binomial coefficients that says that when you have, so let me just write it down in general over here. So k choose k plus 1 choose k plus n choose k. This turns out to be n plus 1 choose k plus 1. And the reason is because you can think of this, you know, it's a double counting argument, this blue thing over here, where you say, how many k plus 1 subsets can you choose from an n plus 1 set? The answer is there on the right-hand side, quite obviously. And on the left-hand side, you add up those subsets again, but in a slightly different way, where you divide them up according to the standard argument is according to the largest largest element in each subset. And so anyway, you have this identity over here, and when you apply this to all this stuff over here, so now you take this and you plug it in here. This is getting very disorganized, which I apologize. Okay, my goodness. So let me just move this. Oh, okay, over here. Yeah. So this is then n plus 1 choose 3. So there we go. So that's the Wiener index of, and that should have said Pn, not G in general. So okay, so there's Pn there. And then to get the average distance, and now okay, now this is just getting worse and worse. Oh my goodness. Okay, so now I'm going to find some space down the bottom here. So then the average distance of Pn is then n plus 1 choose 3 divided into n choose 2. And if you do the arithmetic there and work it out, then it comes out to be n plus 1 over 3 as desired. So that's the first thing. Let me just see. I thought I saw something happening in the chat or something like that. Let me just see. Oh no. So this is just so okay. So just replying to James in the chat, yes, I think that's a good way to go about it as well. So you progressively pick vertices off a tree and move them further and further away from along, you know, put them onto the ends of a diametral path or whatever. And when you do that, you show that the things get progressively bigger. Okay, so there is the first part, which is the fact that the average distance of Pn is n plus 1 over 3. And now what one can do in order to take the next step, which is to show that this is actually the worst case scenario, and that when you have a graph in general of order n, that the average distance of that graph is bounded above by the average distance of Pn. So let me just clear this whole thing. There we go. It just disappeared. It's just gone. What one can then do to show that the average distance of a graph of order n in general is less than or equal to n plus 1 over 3, which is the average distance of Pn, is do this by induction on n. And so you start off, and I'm not going to go through the whole argument here, just mention some of the highlights. So if one starts off, for example, with so if n is, so okay, so take n equals 2 as our base case, and so n equals 2 as our base case, then you know G is a connected graph of order 2, so therefore it's P2, and then we're okay, right? So then we move on from there, and we assume that we've got a graph of order n. So here's a graph of assume the result is true for graphs of order n minus 1 or less, and then we've got a graph of order n. So there's our graph of order n. Yeah. It doesn't look like a graph, but it is. So I'll draw some vertices and so on and so forth. And now one of the things to realize, and this is something which Peter talked about in his talk as well, is that if G is not a tree, so then G contains some cycles, and edges on cycles are not bridges, and so that means you can delete one or more edges in the graph and get a graph which is still connected. And of course, when you delete an edge in a graph, the graph is still connected. The distances between the vertices can only increase, and so the average distance can only increase. So we can assume. So G is a tree, and this is useful, of course, because it's a tree, so we can take. So here's the tree here. This is my favorite tree for the time being, but I can't guarantee that if you ask me tomorrow, it will still be my favorite tree. It might be by then I've gotten a favorite tree. So what we can do is pull off an end vertex. So take this vertex here. So call that vertex U, and then delete this end vertex. So you get a pair of scissors and you cut through this edge. What's left, because you're removing an end vertex, is a connected graph of order n minus 1, to which we can apply the inductive hypothesis. So now we get that the average distance in that part over there, so this is mu of G minus U, is at most n plus 1 over 3 from the inductive hypothesis. And then it remains to see what happened, what the effect is when we add back in this edge over here. Well, if we think about it, when we're adding up all of the distances between the vertices in this graph, each pair of vertices is either it's a pair of vertices which are in this red thing over here. So that vertex and that vertex, for example, in which case we've already accounted for it with this over here, or it's the distance between you and some vertex in this red part of the graph. And so then we just need to think about what's the worst that can happen when we're adding up all the distances from you to the vertices inside this red part of the graph. And so if this is you here, so let me just, so there's you there, yeah, so you've got some vertices over there. So this is what Peter called N1. These are adjacent to you, and some other vertices there in N2, which are adjacent to these vertices. So these are the ones at distance 2. These are the ones at distance 3, and so on and so forth, all the way out to the ones which are just maximum distance from you, whatever that is. So there we go there. And then what you want to do in order to maximize that sum, of course, is you want to move the vertices out as far as possible. So if there are 2 vertices in here and 2 vertices in there and 3 vertices in there, if you instead you take these vertices and you start stringing them out as far as possible, so you have exactly 1 vertex in each distance layer as you go out, then you get as big a sum as possible when you're adding up the distance from you to all of these vertices. So then the distance, so let me see here, the distance from you, or rather the sum of the distances over all the other vertices x in the graph, is at most, the biggest it can be is if you've got only 1 vertex adjacent to you and only 1 vertex at distance 2 from you. And that's why did I put a comma there? Hang on a second. Oh, where's the end? And only 1 vertex at distance 3, and so on and so forth, all the way out to only 1 vertex at maximum distance from you. So, and that would be all the other vertices in the graph. So that would be n minus 1. n-1 vertex. So now, colleagues, ladies and gentlemen, as I said, I don't want to go through every detail of the proof, but if you now take these two things here, so you take that, and you take this, and you put the two of them together, and you do some algebraic manipulation, then out from that pops the end of this inductive proof, and you see that the graph G, the one we started with, must have average distance at most n+1/3. Sorry, my place. So I see the message in the yeah. So absolutely. Sorry, my apologies. Yeah, because G minus U has n-1 vertices. So yes, you're absolutely right. Sorry. Let me just do that. There we go. Okay, thank you for the correction. Let me just see if I. Yeah, that's right. Okay, so defining. Okay. Okay. Great. So let me pause there. Any comments, thoughts, questions, suggestions, criticisms? I've been following what people have said in the chat. Anybody got any other interesting ideas about how to tackle this problem? Okay, I don't see any hands or any voices raised in indignation or with interesting remarks or anything. So let me just back out of this for a second. Where's the stop sharing button? Oh my goodness! Oh, there we go. It was hidden underneath the thingy bar. Okay, so let me just pull this up again. There we go. Okay. So that was the first problem there. So the second problem. So once again, we're talking about the average distance, and in this case, we have a balanced bipartite graph. So balanced bipartite graph one in which you've got two sets called the partite sets. And there are no edges inside this set. The first, the left-hand one, the left-hand partite set, and there are no edges inside the right-hand partite set as well. So all the edges in the graph go between the two partite sets. That's what a bipartite graph is. And this bipartite graph has the additional property that it's balanced. So the number of vertices in the left-hand partite set and the number in the right-hand partite set are equal to each other. And the question here is to find a lower bound on U of G. So let me pull up my whiteboard again. Guess I've got to stop sharing here first. Okay. Cannot share screen. Oh, okay. No, I stopped sharing the screen. I asked myself to stop sharing the screen, and then I'm going to share the screen again. So, yeah. But it said other people, right? You can't share the screen while other people are sharing the screen, but it wasn't other people, it was me sharing the screen. So it was a little bit off. Okay, so we've got a balanced bipartite graph, and that's, hang on, that's the wrong color. Let's see if I can make this whiteboard more organized than the last one. So a balanced, and I almost wrote balanced whiteboard. Okay, now hang on. So balanced bipartite graph. But I want the whiteboard to be balanced as well. So balanced bipartite graph, as previously indicated, you've got these two partite sets. Right, so there are all the vertices. And and there are n over 2 vertices on the left and n over 2 vertices on the right. So if you call the left-hand partite set L and the right-hand partite set R, and you start looking, as we did in the previous question, at the Wiener index. which is the sum of all the distances in the graph. And then when we get to the end to find the average distance, we just take the Wiener index and divide by n, choose 2. So we've got 3 different kinds of distances between vertices here. We've got distances between vertices in L. We've got distances vertices in R, and then we've got distances a vertex in L and 1 in R. Now so let's talk about these one at a time. So 1 and 2 and 3. And so if we take 2 vertices in L, so there they are there, because this is a bipartite graph, as I mentioned previously, that means there are no edges inside the partite sets. So that means that the distance between any 2 vertices in L is at least 2. Right? So the distances between any 2 vertices in L is at least 2, and there are n over 2 choose 2 pairs of vertices. So we've got so let me just say W, by which I mean the contribution to the Wiener index from pairs of vertices which are both in L is at least 2 times n over 2 choose 2. And similarly, so of course for R this is the same. So for R the contribution is once again 2 times, at least 2 times n over 2 choose 2, because there are n over 2 choose 2 pairs of vertices we can look at there. Okay, so what about number 3? So now we look at distances between a vertex in L and a vertex in R. So if I just get my, so let me just delete those. No, oh my goodness. Okay, hang on. Okay, there we go. So then so now if we look at a vertex here, so there we go, and a vertex here. So there are loosely speaking 2 possibilities. I mean, there might be an edge between these 2 vertices. But if there isn't an edge between these 2 vertices, right? So if there's no edge between this vertex and that vertex, it's not possible that those 2 vertices can then be at distance 2. Because in order for them to be at distance 2, so for example, if hypothetically speaking, if there's a vertex there somewhere which is distance 2 away from this vertex, then you'd either have to go across here to a vertex there, which then goes to this vertex, and that's a problem because this is a bipartite graph, and there are no edges in that partite set. Or you'd have to do the same thing over here. So you have to go here somewhere and then across. And those 2 things can't happen. So we have 2 possibilities. And those 2 possibilities are, when we're looking at pairs of vertices in distinct partite sets, that they're either at distance 1 or they're at distance at least 3. So if we look at the contribution we get to the Wiener index from those possibilities, well, there are m edges in the graph. Right, so that means that there are m pairs of vertices, which we get a contribution of 1 from. So let me just to make clear what I'm doing there, then put a 1 times m. So the m pairs of vertices at distance 1, and then from the remaining. So what have we got here? We've got n over 2 vertices on the left-hand side, n over 2 vertices on the right-hand side. So that's that number of pairs we can choose, and then all of those vertices, except for the m pairs we've already talked about, are at distance at least 3. So the contribution to the Wiener index from pairs of vertices that are in distinct partite sets is at least 1 times m plus 3 times, and then so n over 2 times n over 2, that's the number of pairs of vertices we can pick from with one vertex in L and one vertex in R, minus the ones which we already accounted for, and all those are distance 3 at least apart. So we get this over here. And now, colleagues and ladies and gentlemen, if we take all of these things, so let me just, so this slide is much better organized than the last one, isn't it? I mean, wow, this is quite something. Yeah. If we now take this and this and this and add them all up, that gives us a lower bound on the Wiener index of the whole graph. And then if we do some algebraic manipulation again and divide by n choose 2, then we'll get a lower bound on the average distance of that balanced bipartite graph. So let me pause there for a moment and ask if there are any thoughts, comments, suggestions, questions, corrections. So let me just have a look. So I have a whole bunch of questions that just popped up in the chat. Does this work for multipartite graphs as well? So if you've got a multipartite graph and then you add up the distances in each layer, and then you take the distances between vertices in different partite sets. Yeah, I mean, so it's a little bit different because what you could have there was if you've got a multipartite graph. So say something like this. So for example, you can have, if there's a vertex there, you can have a vertex which is distance 1 away from a vertex in this partite set, but you can also have a vertex which is distance 2 away, because you can go via another partite set and into there. Right, so there is a difference there, but my guess is, not having worked through the whole problem, of course, is that one could use this in order to find a bound on the average distance of a multipartite graph in general. Is the lower bound sharp in general? That's an interesting question, Brandon. So if you've got a complete multipartite graph in which you've got all the edges going back and forth from left hand to right hand side, then this should be sharp, unless I'm missing some detail. So for a complete multipartite graph, in which balanced multipartite graph in which every vertex on the left is adjacent to every vertex on the right, so in that case, there would be no pairs of vertices at distance 3. So everything would be at distance 2 or distance 1, and then you should get sharpness. Can we do a similar argument for any independent subset of V where I is the independence set? Shaheen, I'm not quite following your question. Can you, unless, hang on, maybe you've clarified it later on. Okay, so Shaheen, so I'm not quite sure about your question. Maybe I'm not quite what you're saying, but maybe you can send me an email or something, or ask. Has an independent set of vertices. Okay, so I mean, a graph always has an independent set of vertices. So you mean if you start with an independent set of vertices, and then say the distances within the vertices in the independent set are at least 2, and then the distances from the other vertices, well, so that will be at least 1. I mean, yes, I guess one could use that to get a bound as well. Let me see if there are other questions. Okay, we're running kind of later than I thought. So let me just move on to the next one, and I want to leave a little bit of time to talk about this research problem at the end. So let me talk about this one sort of quickly. So let me just stop sharing my screen. Okay, and so then the last question. Wrong part of the screen. Oh my goodness. Okay. Okay, so there we go. Determine the largest possible diameter of a 2-edge connected graph. And so this is once again similar to suggested by Peter and similar to some of the things he talked about in his talk. So let me stop showing the largest possible diameter of a 2-edge connected graph. Let me pull this up on the screen here and clear all this stuff here. So okay, so the largest possible diameter of a 2-edge connected graph. Okay, and 2-edge connected, of course, and I'm sure everyone knows this anyway, means that there are no bridges. So I'm not going to go the whole way through this one. I'm just going to sort of sketch it because we're a little bit. I want to move on to the next thing, but and this is similar to some of the arguments that Peter used in his presentation. So what one can do is say, well, take a vertex of maximum eccentricity. So let's call this U, and look at all of the distance layers as you go out from U. So this is following Peter's notation. This is N1, N2, N3, and N4, ND minus 1 and ND, where D is the diameter of the graph. So just to be clear, I should say here that that's D, right? And this is N0. And so okay, and then we've got these edges, and the key thing, the key point, and this is similar once again to some of the arguments in Peter's talk, is that if whenever you've got two of these things consecutively, so for example, if you've got N3 and N4, whenever you've got two consecutive distance layers, you can't have both one vertex in the first one and exactly one vertex in the first one and exactly one vertex in the second one, because if you do, then the edge between them is a bridge. Right? So whenever you've got two consecutive distance layers, you can't have exactly one vertex in the first one and exactly one vertex in the second one, because if you did, then the edge between them would be a bridge, and this is a 2-edge connected graph. So that means that in any two consecutive, not consecutive, consecutive distance layers, no, that's, oh my goodness, yeah. There are at least 3 vertices. And then what one can do, so that then one just exploits this to count things. And what one can do, for example, is one can say, well, the number of vertices in the graph is n0 plus n1 plus n2 plus nd minus 1 plus nd. And so therefore, 2n is n0 plus n0 plus n1 plus n1 plus n2 plus n2 plus n3 plus plus nd minus 1 plus nd plus nd. And then if you think about the things of each of these things is at least 3, and you put everything together and you think about the fact that n0 is 1 and nd is at least 1, then everything pops out the other side. I'm going to leave that one there, so you must fill in the rest of the details. Are there any questions, comments, criticisms, concerns, convolutions, ad hominem insults? This is the right time of the day for that kind of thing as well. Okay, I'm not seeing any hands or hearing any voices raised in anger or excitement. So let me just wait 10 more seconds, and then I'll move on to the next thing, which is the as far as I know, unsolved research problem. Okay, so let me shift onto the okay, so I'm going to stop sharing my screen here and go back to my set of slides. Okay, so I can see that on my evil me computer, so I'm assuming everyone else can as well. So what I want to do now is just talk very briefly about this problem. So this is to do with what are called eccentric subgraphs. And as I said, this is stuff which has been accepted for publication but hasn't appeared in publication yet. So it's more or less hot off the press. Although it's been a problem which we worked on for a long time before we got around to sending it off for publication. So this is something which is inspired by the idea of an eccentric sequence. So if you remember an eccentric sequence, you arrange the eccentricities of a graph in some order and then ask under what conditions is it, for example, there's a sequence of positive integers, the sequence of eccentricities of a graph. And so you can take that one step further in a sense, and say, well, in addition to having a bunch of eccentricities, let's draw in the structure of the graph we want as well. So for example, so there's a graph there, labeled graph, right? So that with some labels on. So I've got a C5 and I put some positive integers on some of the vertices. And then you can ask the question, can you find a graph in which that C5 appears as an induced subgraph, and in which those labels are actually the eccentricities of those vertices? Right? And the answer for that particular graph with those particular labels on is yes. So if you look at this, so I've added some additional vertices on here. So notice this is, so G, the original graph, there it is, is an induced subgraph of this graph. And now if you look at each of these vertices here, so let's look at this one, for example, and say, what's the eccentricity of this vertex? Well, it's distance 2 away from there, 2 away from there, and distance 1, 2, 3 away from there, 1, 2. Okay, so the eccentricity of this vertex is 3, which is what the label was to begin with. This one over here, is that eccentricity 4? So 1, 2, 3, 4, 1, 2, 3, 1. Yeah, so the eccentricity of this vertex is 4. So what we've done is we've embedded this labeled graph inside a bigger graph in such a way that the labels on the vertices become the eccentricities. So when we can do that, that original labeled graph, the C5 with those red labels on, is called eccentric, right? So a graph is called, G is called eccentric if you can find a connected graph H so that G is an induced subgraph of H, and in H, the eccentricity of each of the vertices in the original graph G are the labels that were on them originally. Now, you know, the obvious problem here is to determine necessary and sufficient conditions for a label graph to be eccentric. And I'm happy to tell you that problem has been solved. But bear with me. I'm mentioning that because, you know, I'm getting to telling you about a related problem which hasn't been solved yet. The reason this related problem hasn't yet been solved relates to the way in which we solved this problem. So let me talk about necessary and sufficient conditions for an arbitrary labeled graph to be eccentric. Suppose we start with that labeled graph there. I'm going to tell you, looking at that labeled graph there, I can tell immediately that it's not eccentric. So it's not possible to embed that labeled graph inside a bigger graph in such a way that that's an induced subgraph, this one here, and so that those red labels become the eccentricities of the vertices. It's not possible for that labeled graph. Can anyone tell me why? Yeah, 4 and 6 are too far apart. Yeah, so there's an elementary result on eccentricities, and I don't remember, Peter, whether you mentioned this in your talk, but whenever you've got a graph, adjacent vertices can have eccentricities that differ by no more than 1. Right, and here we've got, in fact, 2 pairs of vertices, so that 4 and 6 are adjacent, but their eccentricities differ by 2. And 3 and 5, similarly, there's a similar problem over there. So this, ladies and gentlemen, colleagues, that is not an eccentric labeled graph. Here's my next problem. So I'm going to tell you now that one is also not an eccentric labeled graph. It's not possible to take G2 and embed it inside a graph in such a way that those red numbers become the eccentricities of the vertices. It's not for the same reason as the first graph, though. I mean, all the vertices there have labels that differ by no more than 1. So what's the problem? Now, see, hang on. So I'm looking at chat here. The 1 should be adjacent. Yeah. So a vertex which has a label of 1 on, like that one over there. So in a hypothetical graph in which it's embedded so that 1 becomes an eccentricity, that means that it's distance 1 away from everything. And remember, when we're embedding G2, G2 has to be embedded as an induced subgraph. So we're not allowed to add any edges, which means that if there's a vertex which is labeled 1, it must already be adjacent to everything. So this is not an eccentric subgraph, sorry, an eccentric labeled graph, because it's got some vertices in labeled 1, but those vertices labeled 1 are not adjacent to everything else. Okay, so here's my next example. Here's a graph, and I'm going to tell you that once again, this graph, and I see Stein has already spotted the problem. This graph is also not something that can be embedded inside a bigger graph so that those red numbers become the eccentricities. And the reason is because, as Stein has already said, there's another classical result, which I remember Peter did cover, which is that in a connected graph, the diameter is less than or equal to twice the radius. And what that means is, if you think about it fairly quickly, then you'll see that in a graph like this, where these labels are supposed to become the eccentricities, that the smallest such label, which we call L min, and the largest such label, which we call L max, that there can't be a factor of more than 2 between them. So L max can't be bigger than 2 times L min. Okay, so there are 3 label graphs that have 3 different issues with them that prevent them from becoming eccentric graphs. And what's surprising, actually, is that that's all you need to take care of. So this is a theorem from our accepted but not yet appeared paper, which I've called Kelly's theorem, because the principal idea in the proof was from one of the authors from Kelly Guest. And so this says that not only are those conditions necessary, those three conditions there, right? So adjacent vertices have to have labels that differ by no more than one. Every vertex which is labeled 1 must be adjacent to everything, and the largest label can't be more than twice the smallest label. So those conditions are not only necessary, they're sufficient. And they're sufficient even more powerfully that, so that you can pick any pair RD of positive integers with D between R and 2R, and Lmin and Lmax between R and D, and you can find a graph H of radius R and diameter D such that G is eccentric in H. Okay. So there's the general theorem, and there are the conditions, the necessary and sufficient conditions for a graph to be eccentric. Well, so what? Okay, well, here's the unsolved problem. The proof that we have that works in general for graphs to show that if you have a graph, a labeled graph that satisfies these three conditions, then you can find a bigger graph containing it, so that the smaller graph becomes is eccentric in the bigger graph. That proof, there are two different steps in the proof, which is basically a construction, in which what we're doing will in general produce a graph which is not planar. There's a step at the beginning where we heterodyny the graph. So we take, in general, take a graph, and there's this classical construction due to Steve heterodyny that shows that every graph is the center of a graph. And so what you do is you take 4 vertices, you turn them into 4 vertices, 2 copies of K2, then you pick one vertex from each of those 2 K2s, and you join them to everything in the graph. And that gives you a graph of diameter 4 and radius 2, in which the graph that you started with is the center of that graph. Okay, so we start doing that at the beginning of the construction, and then little bit later things get worse, because then we take that graph and we do something called a strong direct product with another kind of graph, and both of those things have the potential to produce lots and lots of edges which disrupt planarity. So the key takeaway is the construction we have that works in general doesn't work in general for taking a planar labeled graph and embedding it inside a planar bigger graph. So this is the question I'm putting to you here. I want to add a asterisk. So this is not a question I have time to work on myself. I think it's an interesting question, but as I said in the other talk I gave yesterday, my time for research has become very, very shrunken in the last couple of years. So I'm putting this out there as something which I think is interesting. But it's not something which I'm going to be participating in. I think it's an interesting problem, but not one which I'm going to be working on myself. And if you're interested in this, the first step I think will be to look at the paper. So there's the paper there on subgraphs with prescribed eccentricities. I'm happy to send copies of the preprint to anyone who wants them. But although I'm not going to work on this myself, I'm certainly be interested if somebody finds a solution to this problem, finds necessary and sufficient conditions, or proves that these necessary and sufficient conditions work for planar graphs as well, inside bigger planar graphs, and that you just need a smarter construction in order to guarantee that everything works as advertised. Let me just look in the chat and see. No, so James, just to reply to your question, no. So I mean, there is a similar thing, of course, for making making a graph into the center of a bigger graph called the central appendage number, and this is also an interesting question which could be asked for this. It hasn't been asked yet that I'm aware of. We didn't look at it. What we did in the paper, we looked at the result there. We've got another section where we look at what we call strictly eccentric, where you want to have all of the eccentricities of in particular ranges appear in the graph that you prescribe. So for example, if the graph you start with the labels on has vertices with labels 5, 6, and 7, then those must be all the vertices with eccentricities 5 and 6 and 7 in the resulting graph. So that's a stronger thing called strict eccentricity. And then we also looked at embedding trees inside trees. and that we got some nice results on as well. But that's another interesting question you're posing there. It's a natural question to consider.